Hi, I'm Chris McCreary. I'm the founder and director of the Northern Ireland Science Festival. You're very welcome to this digital edition of the festival, and tonight we're delighted to present one of our headline events. It's Dr Katie Mack speaking on her book, The End of Everything, and she's going to be in conversation with the festival favourite and brilliant Jim Al-Khalili. A big thanks must go to the Institute of Physics for sponsoring tonight's event, and if you do like what you see, please make sure to hit that like button, hit subscribe and follow us for more content. Thank you.
Hello and welcome everyone to this event at the Northern Ireland Science Festival, albeit remotely. It's a pleasure to be here. Before we start, I would like to thank the Institute of Physics Ireland for sponsoring this event. I think we should just get started. So it's an absolute delight to be welcoming Katie Mack. I think, Katie, this is your first appearance, albeit virtually, at this festival.
Yes.
And it's a shame we can't be there in person because we were just talking before we started recording. Just what a great event it is, you know, to be there. It's such a buzz. I've been at the Northern Ireland Festival for I mean, this is probably my third or fourth appearance, but the others were obviously physically there, and you just get such a buzz from the audience there. So it's a shame we can't be there, but hopefully we can come back next year. Okay, well, I should introduce you first. So Katie Mack is a theoretical cosmologist. She's based at North Carolina State University, but worked all over the world and at some of the leading institutions, certainly in theoretical physics in the world: Caltech, Princeton, Cambridge. You and I have a colleague we both know very well, Andrew Ponson. I think you shared an office with him at Cambridge. I know Andrew very well.
Yeah, we did.
And of course, you've worked with many of the big thinkers. You are, of course, one of those big thinkers, but many of the giants in the field. We're here at this event basically to talk about your new book, The End of Everything. And it really is sort of the end of everything. I think it's fair to say that certainly until the last century, until Einstein, I guess, talking about eschatology, that's the right term, isn't it? The end of the world.
Yes.
Really was the domain of theology. Now, scientists and cosmologists are taking center stage.
Yeah, exactly. I mean, it's cosmology in general was sort of the realm of theology for a very long time, and at some point it became acceptable and reasonable to talk about the beginning of the universe, and there was sort of evidence that was a thing that happened. But the end of the universe has been something that's sort of only slowly gotten into the consciousness of physicists as a reasonable field of study. And I think one of the interesting things about it is that part of that has been driven by studies at the beginning of the universe, where it's been clear that there are connections between how the universe began and how it might end, and that this is all just part of the big picture of what is the story of the universe, what is the structure of the universe, what is really, what is it all about, how does it work fundamentally?
And that is essentially what we call cosmology. I guess that cosmology as a term goes back millennia, people talking about the totality of everything, but it really became a proper science. Whether it's a part of physics, maybe let's say physics is all encompassing cosmology, but as you say, cosmology is the structure, the evolution of the whole universe. Now, when we talk about the end of the world, people tend to think about the end of our planet. When the sun finally runs out of its nuclear fuel and becomes a red giant and it engulfs the Earth, or certainly fries everything on Earth a few billion years from now. What you're dealing with is much longer term than that. Never mind our puny planet. It's the totality of everything. How is everything going to end? That's a more ambitious sort of undertaking, isn't it?
Yeah. So in my book, I do away with the Earth on page 1. I think that's very much near term future. But the thing that I've been fascinated with, and that I wrote this book for, was how the entire cosmos will end, and it's oftentimes when you bring that up, just to the public in general or something, a lot of people will be like, oh, the cosmos is forever. That's not gonna end. But as we understand it, as we understand the evolution of the universe, it does change over time. It was very different at the beginning. It's different now, and it'll be different in the future. And as our understanding has evolved on this, it really appears that there's kind of no good ending for this. Like the universe will continue to change in such a way that it'll become more and more hostile to the existence of structure, of life or intelligence, or just any sort of meaningful things. And there are lots of different ways that could go. And so in the book, I explore sort of 5 of these different categories of endings, but all of them have in common that there will be a point at which everything in the universe, at least, is over. And that's a fascinating idea to me, because it is sort of this unsettling idea that that all of this that we consider to be just what we live in, just the background state, like that is fundamentally changing all the time, and changing and evolving towards something very different.
I was going to ask you why, because I think probably a lot of people would be thinking, why is this something that's fascinating to you, given that we're talking billions, probably trillions of years in the future? Most people are just thinking, how are we going to get through the COVID pandemic? Am I going to go on a holiday this year? Never mind what might happen trillions of years from now. So what is the motivation here, the fascination?
I think that part of it is just that it is the this big picture. It is this the sort of really understanding our story as a universe, our story of existence, involves understanding the ending. And there's part of me that just kind of, you just kind of want to be able to wrap it up in a bow and say, okay, this is how it started, this is how it'll end, this is where we are in that narrative. And so I think it's just this sort of basic question that humans have of, what's going to happen next? Where are things going? How do we fit into this picture? So that's part of it. And then from a physics point of view, this topic really encompasses all of the big and exciting mysteries in our field, things like dark energy, dark matter, the early universe, and the mystery around how it began, which could tie into the ending question, and then even things like the Higgs boson discovery and how we're understanding particle physics. That also comes into this question of how the universe will end. So that it's, from a physicist's point of view, all the most exciting stuff gets wrapped up into this question. And from a sort of personal point of view, I think it's really just trying to really conceptualize and understand that picture. And then, you can get into some deeper stuff around how does it affect your sense of meaning if you're living in a universe that's going to end. And that's something that I've also spent a lot of time thinking about over the past couple of years for this book.
Do you find maybe at social gatherings, that you depress people, because this is, cosmology talking about the end of the universe. It's a secular view as opposed to, a theological picture. But it's, the fact that what will happen, and it's a rather bleak. I mean, we're going to talk about the 5 different scenarios you discuss in the book. None of them are particularly uplifting. The only positive is that it's a long way off.
right
But do you get accused of sort of thanks for cheering us up, Katie?
I think so it's definitely the case that I've sometimes given public talks where I talk about the heat death of the universe, which is sort of the most likely ending, where people just get this look on their face like, what are you telling me? Like, this is awful, and one woman sort of put her head in her hands in the front row and just like, I'm like, I'm really sorry. Like, I don't mean it for it to be like this. So occasionally people do have that reaction. But I think that more often people sort of look at me funny because I seem to take too much joy in thinking about these things. So I get a lot of comments about how much my eyes light up when I discuss the end of the universe. But I think most people, it is a really long way off, and there's a sort of, it's a sort of thrilling idea to think about it. And I think that you can get into a kind of depression or fear sort of situation if you sort of ruminate too much. But I think most people are just curious and fascinated. And I've certainly heard people tell me that the book is not depressing, that they found it to be sort of weirdly calming to think about everything just coming to an end in some way. So that's encouraging. But yeah, there's I'm a little careful about how I talk about it if there are children in an audience, for example. I don't want to traumatize anybody. So you do have to be it's a little bit delicate sometimes.
Well, the book certainly is fascinating. I would normally, on occasions like this, hold up a copy of the book. You should do it.
I've got both the sort of UK edition.
Because the UK and US edition tend, they've got different covers.
So
same title, right? Okay,
yeah, same title.
That's good. The book is on order, but it hasn't arrived in time, so I had to download the Kindle version and read it, which isn't quite the same thing in terms of visuals and showing people. Yeah. I certainly absolutely love the book. I mean,
thank you.
As a fellow physicist and science writer, there are things that I recognize of, this is how we explain the cosmic microwave background and the various technical things. And, but there's some very refreshing and novel new ways, which I guess you must be quite proud of in how to get across what are very difficult concepts. And I think the real skill in writing something fresh about a subject that others have written about is not only to bring it up to date, our current understanding, but also to find new metaphors, new analogies, new ways of getting a non-expert, because that's what this is. The book is aimed at everyone, right? You don't need to have a background in physics to understand. You need to sort of put your thinking cap on to concentrate. But it should be appealing to everyone.
Well, thanks. I really appreciate that. As someone with your experience and how much you've accomplished in this area, it means a lot to me that you found this.
Well, of course, I'm not a cosmologist, so I mostly work on the tiniest length scales in mechanics rather than the grander scales. So,
but those are so intertwined.
They are absolutely now. Absolutely. They really are coming together to understand that the building blocks we need to look out there, and to understand what's going out there, we need to look at the building blocks. That's what makes it all fascinating at the moment. Yeah. So, I guess before we talk about these different scenarios for the end of the universe, maybe you can say something about how is it that we're able to even contemplate? There's so much we don't know about the world, but there's also so much we do know. What is it that has changed in our understanding that has allowed us even to ask and potentially answer this question?
Well, I think that part of it is that we just have so much more data about the universe in general. So we have so many measurements of the way that the universe is expanding. So, this was discovered in sort of the 1920s, that the universe is getting bigger, that distant galaxies are getting farther away from us. And the precision with which we've been able to measure that, measure the rate of the expansion, the history of the expansion has just been mind-blowing. And we're able to measure how much of the sort of quantities of the components of the universe to extremely high precision now, with things like the measurement of the cosmic microwave background, which is this afterglow of the Big Bang that we can study to learn about everything in the universe. And that's really a precision subject now. So we just have a huge amount of data, and we're able to really piece that together. And the key, I guess, is that we are learning more and more about the history of the universe, and we have sort of this theoretical framework that allows us to then extrapolate into the future. And right now, we're at a really interesting stage with that, which is that we have a very, very good understanding of the history of the universe to, something like a microsecond after whatever the beginning was. We really know what was going on in the past of the universe. We know how the universe has been evolving. And right now, our data sort of suggests a few branching paths for the future. And there aren't that many possibilities for how things could go next. And we're just right at the point where we have these possibilities, and we can't yet say with certainty which way it's all going to go. And so that's why we're at this really fascinating point. And at the same time, we have these big theoretical uncertainties, these big theoretical problems where we have a really good picture of particle physics, we have a really good picture of cosmology, we have a really good picture of how gravity works, and all of them are a little bit inconsistent in some ways. And we don't know how we're going to piece that together. We don't know how we're going to solve those inconsistencies. We don't know what the next theory is going to be that's going to sort of tie that all up and fix all the problems. And so it really feels like we're sort of right at the edge of what will be, a really big leap in our understanding as soon as we are able to kind of piece that all together. And so it's kind of a fascinating time to be thinking about this.
And it's certainly things have changed in the 21st century, our understanding of the universe. When I studied physics back in the 1980s, and certainly all the way till almost the end of the 20th century, the textbooks on cosmology were, I think, painted a picture that is simpler than the picture we now think is reality. So maybe you can say, what we thought might happen and you will, I'm sure, explain the relevance of this pre-1998, which was a key year.
Yeah. So before 1998, there were kind of three possibilities that we could think of for how the universe would continue its evolution to the future. We knew that it had been expanding since the Big Bang. We knew that the Big Bang was this big event that set off the expansion, and the expansion has been slowing, right? So we knew that the expansion had been slowing since the Big Bang. And we wanted to know how quickly the expansion was slowing down. Where the slowing was due to the fact that there's gravity in the universe, galaxies are pulling toward each other. And so something would have kicked off the Big Bang, set off the expansion. Then since then, there's this gravity sort of putting on the brakes for the expansion of the universe. And so the question was, is there enough gravity that slowing is fast enough that everything will recollapse? Or is it just going to slow down the expansion such that the expansion will keep going forever, but always be slowing down? Or is the gravity really so little compared to the expansion that we're just kind of coasting, and then the gravity basically becomes unimportant? So there's sort of three possibilities, like, slowing down so quickly that we're going to collapse, slowing down enough that we're always slowing down, but we're never going to really collapse. We're just right on the edge, or we're sort of heading to this sort of coasting universe where we're just going to keep expanding at basically the same rate forever. And so there was this big effort to measure that. Which of these three possibilities is there? And astronomers were trying to measure what's called the deceleration parameter. How quickly is the universe slowing down? Is it going to recollapse or not? And then 1998 comes around, the measurements come in, and it turns out that the universe is not slowing down at all. The deceleration parameter is negative. The expansion of the universe is speeding up, and that just totally, changes everything. Because what it means is that there's some new component or process in the universe that is causing the universe to speed up in its expansion, which is very counterintuitive, because we only know of things that could cause it to slow down. We know that mass and energy have gravity, they pull together. All of those things should conspire to slow the universe down. And we didn't, there was just the Big Bang. So we know that should be what sets off the expansion, but we didn't know of anything that could cause more expansion as you go. And so we had to write in this new component of the universe called dark energy, which is something that makes the universe expand faster. That's constantly expanding space, over time, even now, in a way that we just didn't know was possible. This was not something we expected at all.
Certainly, I mean, I guess of all the discoveries that have been made in physics, astronomy, cosmology, in my lifetime, that particular observation, 1998, the universe expanding ever more quickly, is the most unexpected. Everything else was sort of, gravitational waves, Higgs boson. We sort of expected that, and it was just like a box ticking exercise. This, who ordered that? It really was completely out of the blue, wasn't it?
Yeah, absolutely. I mean, and in a funny way, because our best idea now of what that dark energy might be actually is something that Einstein first came up with back in the early 1900s. He was thinking about the evolution of the cosmos, and he realized that all of these galaxies and things should be pulling toward each other. Although at the time, I think he didn't even know they were galaxies, just stars.
Right.
We had a much bigger, smaller picture of the universe at the time. But he knew that gravity should be pulling things together, and he knew that we hadn't collapsed yet, and he didn't know about the expansion of the universe, didn't know about the Big Bang. And so he was trying to find some way that gravity wouldn't have made the universe already collapse on itself. And so he wrote into his equations of gravity this term called the cosmological constant, which would sort of stretch out the universe and balance out the gravity so that things could stay stable, stay in a steady state. And the idea was just to keep the universe from having already collapsed on itself. But then in the 1920s, when the expansion of the universe was discovered, it was clear that the expansion could be why things hadn't collapsed yet, because they're actually moving apart. And so that's why the gravity hasn't pulled everything already together. So he took out the cosmological constant, said that wasn't necessary, started over on the equations. And now, now we're looking at it, it's like, well, actually, we do kind of need something to push things apart. We do sort of need something to stretch out the universe. And so the cosmological constant, this term that Einstein wrote in, which is just basically a property of space that has this sort of stretchiness in it. We had to put that back in the equations, and now that fits the data. So it's a very strange thing where, it was totally unexpected, and yet it was already in the equations if we go back far enough.
So Einstein was thinking of, the universe as a bit like a ball halfway up a hill, and you're saying, well, gravity should make the ball roll down again. So I need something to stop it, to keep it static. And then the Big Bang says, no, someone's kicked the ball up the hill, and it's rolling up, but it's slowing. It'll come down probably, or it might get to the top of the hill, as you say,
right?
And sit there, whatever.
Yeah.
But now the dark energy is like, well, there's a wind blowing the ball uphill.
Something's going on, and the ball's just rolling up faster and faster on its own. That doesn't make sense. It's a good analogy.
So you have these 5 possible different scenarios for the end of the universe. You sort of touched on one already, this idea of the big crunch, that the universe gravity will finally win and pull everything back in together, and the opposite of the Big Bang. Given that we now know dark energy is pushing everything apart ever more quickly, does that rule out the big crunch scenario?
So I would say it doesn't entirely rule out, it rules it out in the sense of the original idea behind the Big Crunch, which was one that didn't involve dark energy, where the universe was just, slowing down from the Big Bang phase and the gravity would pull everything together. That idea, is ruled out. But one of the tricky things about dark energy is we don't know what it is. Dark energy, the cosmological constant is one possibility that is just a property of space-time that just has this stretchiness in it that's baked in, and it'll stay the same forever. That's one possibility, but it's also possible that dark energy is some new sort of energy field in the universe. We call it a scalar field, something that would change over time, that would act on the sort of expansion of space differently at different times. And if that were the case, we can't say for sure that it's not something that would change to become an attractive force in the future that would pull space back together. And so that's kind of where sort of modern big crunch scenarios come from, is the idea that maybe dark energy could change and reverse its action. And again, because we just don't know what dark energy is, we're still trying to understand where it comes from, how it works. We can't quite rule that out. I wouldn't say it's a popular idea, but it's there are some scenarios where you could have something like that, or even I go into it later in the book about bouncing cosmologies, where the universe could undergo some kind of contraction due to something like a scalar field, and those would have something like a big crunch, but not in quite the same way. So
I mean, it's not where we're at now. You say we don't know what dark energy is. We've given this thing a name. It could have been called all sorts of different things. Dark energy is just a sort of placeholder for something. But it's not the fact that we don't know, the fact that there's different possibilities. For someone working in theoretical cosmology, it's not frustrating. Presumably, it's an exciting time to be at, not knowing.
It is. Yeah, it is exciting. I work on a different, my main research is on a different sort of big mystery in the universe, which is dark matter, which really has nothing to do with dark energy as far as we know, aside from they're both invisible and we don't understand them. But it's something where we don't know what it is, and we know how it acts on the universe. We know it sort of is this extra gravitational component to galaxies and clusters and so on. And so it's some invisible stuff that's out there, but it's a mystery. We don't know what it is. And that's great, because it means we get to have new creative ideas about it. We get to test it, we get to study it, we get to find ways to learn about this thing, and hopefully it'll lead to a better understanding of the universe as a whole. And it's the same with dark energy. You know, we don't know what it is, we don't know where it comes from, but we do know that if we understood it, it would tell us something really deep about how the universe fits together. And so it's definitely an exciting thing to have one of those mysteries, to have a place to look for the new physics, the new ideas, the thing that will take you one step closer to the big, deep understanding. Because if you're in a situation where everything kind of makes sense and fits together, then you don't know what's next. You don't know where to go next. You don't know how to refine your theory, because whenever you refine your theory, it's because you found some inconsistency, or you found the edge of the validity of the theory, and you've pushed on that, and that's told you what's the bigger picture that you're really looking for. And so it's important to have these mysteries so that you can progress.
So the big crunch hasn't been ruled out entirely, simply because we don't know what dark energy might do in the future.
Yeah.
But the second scenario, I guess, is the one you would say is the most likely one. It's in a sense, it's probably the most boring one. The heat death of the universe. A lot of people talk about the heat death of the universe. So maybe you can explain what that involves.
Yeah. So I would say it's the most likely in the sense that it doesn't include any new ideas that we haven't already written down, and we don't already kind of have a vague understanding of how they fit together. So the idea behind the heat death is the universe is made of matter and, dark matter and dark energy in the form of a cosmological constant. And the cosmological constant is just going to continue the expansion of the universe, continue making it expand faster, but the amount of this dark energy is going to stay the same in the universe, in the sense that each little bit of space has its own little bit of dark energy, and it's always the same density everywhere. And so it just means that the universe expands faster and faster, gets emptier and emptier. And over time, because the amount of dark energy doesn't go down over time, even as the universe expands, everything gets diluted away, and there's less and less matter in every part of space. The galaxies get farther away from each other. Over time, the universe gets darker and emptier and colder, and less happens. Stars form less often. The stars we have burn out, black holes evaporate, and eventually you get to this point where there's really just nothing left, when the universe is just this cold, dark, empty place with a little bit of residual radiation hanging around at a very, very low level. And everything in the universe has been reduced to basically just the waste heat of every physical process that's ever occurred. And that's why it's called the heat death, is that you've just kind of decayed everything into this disordered energy that's just thinning and thinning out across the universe.
And that's way beyond sort of the lifetime of galaxies. I mean, galaxies themselves, within our own Milky Way galaxy, if dark energy doesn't start increasing, if it is a cosmological constant, it's constant property of universe, within our galaxy, the individual stars that we can see in the night sky, they're not moving away from us, because gravity is still in control inside a galaxy.
Yeah, exactly. And so the conditions within each galaxy would stay basically the same. I mean, our galaxy, we're gonna collide with our big galaxy next door, the Andromeda galaxy, in about 4 billion years. That'll sort of mix up. It'll be fine. It'll mix up the stars and stuff. There might be a few new stars forming, but it's not going to be. The stars themselves won't collide with each other. It's not like we're all going to go up in a big fireball. But then after that, we're going to be sort of just this isolated, little ball of stars and gas and dust and planets and things. And the distant galaxies, everything, sort of a bit farther away than that is going to be moving away from us with the expansion of the universe faster and faster, and eventually so quickly that we won't be able to see other galaxies anymore. So sometime in the next sort of 100 billion years, every other galaxy outside of the ones we'd already collided with will be so far away that we won't be able to see them. They'll be moving away so quickly that the light won't be able to reach us, and the universe will just get darker and darker outside of our little sort of, mega galaxy. And then the stars within our galaxy will be burning out as well. And so the what dark energy does in this scenario, what a cosmological constant does, is it isolates things. So once something is already bound together by gravity, it stays, but it becomes more and more isolated, which means that you don't have the galaxy collisions that bring in new gas and create new stars. You don't have that sort of constant renewal of things. And so within each galaxy, things just kind of decay and burn out and fade away. And so it's this very isolated, sort of lonely kind of ending, which is I think one of the things that makes it sound so depressing, is that it's really
and it's unavoidable, right? We have this thing called the second law of thermodynamics, which says, there's no way we can carry on. However clever we are as an intelligence, we're not going to be able to maintain order forever.
Entropy increases. The disorder of the universe increases over time, no matter what you do. And so when you reach that ultimate heat death, what that means is you've reached the maximum entropy state of the universe, that there cannot be any more disorder. Everything is maximally disordered, which just means that nothing can ever happen, really. You might have little sort of fluctuations here and there, but there will be no new structure. There will be no intelligence. There will be no processes, really. And that's an ending. It's really
and if people think that that's a really sort of depressing ending, maybe move on to the next scenario, and maybe people think, hang on a minute, give me back the heat death, because suddenly it's not so bad, because there's the possibility that dark energy does change, and therefore there's a different scenario, more dramatic.
So dark energy could be could give us a much more violent end. We already mentioned how if it turns around, it could give us a big crunch. If it just keeps going in terms of making the universe expand faster, but if it's more powerful in the sense that there's more and more of it over time, and it doesn't just sort of stay constant like a cosmological constant, but increases, then you get something called a big rip, which is where even within a galaxy, the dark energy would be building up, and it would be sort of pulling the galaxy apart from inside. And that would mean that, in a single galaxy, you would have the stars at the edges would start to pull away as the universe expands within that galaxy and starts to pull the stars away. It starts to pull the planets away from the stars. And that would just build up over time, such that you get to a point where planets are being ripped apart, where atoms and molecules are being ripped apart, and at the very ending of it, it would sort of rip space itself apart. We don't know exactly what that would look like, but that would be cataclysmic. You get to a point where there's so much dark energy building up that the expansion proceeds so quickly that it just tears space apart completely.
Okay, that's very, very unpleasant to think about. But again, we're talking about trillions of years in the future.
So the timescales here are a bit some of these are a bit sort of hard to conceptualize. When I tried to give some idea of the timescales in the book, but really some of these just don't make sense to the human mind. I mean, the heat death is so far in the future, like, you have to start putting exponents on your exponents to get to the kind of timescales we're talking about. I can tell you that 100 billion years is about when you stop seeing other galaxies, but when the last black hole evaporates is so far into the future, like 10 to the 100 something whatever years. I mean, it doesn't. You stop being able to conceptualize those. And
it makes the life of the universe so far from the Big Bang seem like we've only just started.
Exactly, completely. And then and with the Big Rip is an interesting one, because if if it were to happen, if it really is, if we really are heading that way, there's a parameter we can measure. There's a property of dark energy that we can measure called the equation of state parameter. And if we know that number, and if it's a number that is less than -1, it turns out, then that automatically says that we're heading toward a big rip, and also tells us exactly how long from now that big rip will happen. So what we can say is that based on our current estimates of that parameter, based on our current measurements, that would give us until at least something like 200 billion years from now before something like that could possibly happen. That's within our sort of worst case scenario based on current measurements. But as we get better at measuring how dark energy is working, that time scale will get pushed farther and farther away, assuming that that we really do live in a universe where it's just the cosmological constant. If we live in a universe where we have this phantom dark energy, which is what it's called when you have this dark energy that can get more powerful, then we'll be able to narrow in on that number. But 200 billion years is like, that's sort of the worst case scenario at the moment. And that's, again, long after the stars have burned out and, the universe is already pretty dark. So it's really not something to worry about anytime soon.
And you talk about, as we refine our measurements or sort of predictions of our theories can be tested. We don't want to be waiting 200 billion years to know whether or not the big rip's going to happen. So, what can we measure? What can we learn now that might give us a better understanding of what could happen in the future?
Well, what we really want to do now is understand dark energy, and that involves, it's a bit of a hard thing to measure. Dark energy is a tough one because it seems to be something that its only behavior is to make the universe expand faster. And that means that there's sort of two things we can measure. We can measure the rate of the expansion of the universe, which we do by looking at really distant sources and seeing how quickly they're moving away, and factoring in that light is old because they're far away. And so we're looking at the past. So we can piece together the expansion history of the universe through that. Then the other thing we can look at is the rate that structure has built up. So the rate that galaxies and galaxy clusters and things have formed over time, again, by looking at very distant objects and therefore looking into the past of the universe. And those two things are telling us something about how dark energy has been working on the stretching of space over time. But there doesn't seem to be a whole lot else to measure about dark energy because it is something that really does just seem to work on space on the largest scales. So there's a lot of theoretical work going on about dark energy, trying to put together theories of how it might work and trying to find clues to which of those theories might be valid. And then there are also sort of some scenarios for dark energy that involve things that you can actually detect in laboratories. So if it is this, some kind of scalar field, this sort of energy field through space, then that might connect with new particles that could be detected or new processes that you could see in a laboratory. So there are a few different avenues people are pursuing to understand dark energy, and it's mostly about the expansion history and so on. And that's where we can get measurements like the equation of state parameter. But there's some interesting sort of new creative ways to look for it as well.
Well, okay, so we've had the big crunch scenario, the heat death, and the big rip. Now, the fourth option is one that I didn't know so much about, what you call vacuum decay. So maybe you can, here's the challenge. Can you explain vacuum decay? Not technically. Well, that's your job, right?
Yeah.
So go for it.
All right. So vacuum decay is a really fascinating possibility. And it's kind of it's the one that is my personal favorite and sort of is what prompted me to write the book, really, is hoping to learn more about vacuum decay and bring this idea out there because it is so fascinating and weird and terrifying. And so the idea behind vacuum decay is, so you've heard of the Higgs field, the Higgs particle, the Higgs boson. This is the particle that was detected at the Large Hadron Collider, and it's something to do with how particles got mass in the early universe, right? What really is the important discovery from that is that the Higgs field exists. And the Higgs field is this energy field that's through space. It's a scalar field, which I mentioned before as a kind of energy field that maybe dark energy is something like that. The Higgs field is this energy field that's through all of space. And basically the value of the Higgs field, so what sort of number that energy field takes through space, is connected to how physics works in our universe. And in the early universe, in the very beginning, the Higgs field had a different value. It was set up differently, and physics was set up different. We had a different set of particles. We had different fields in the universe. Particles interacted in different ways. And then a change occurred that changed the value of the Higgs field and set up the physics that we have now. So it gave us, we have quarks and leptons, protons and electrons, and all the particles we have now. All of the interactions they have are because of the value of the Higgs field. It sort of set up physics as it is now, and it's been that way since the beginning. And so we don't want the Higgs field to change again, right? That would be really bad, because it would mean that the way physics works would change, and then our particles wouldn't hold together anymore, and that would be unfortunate. And so what we seem to be finding in experimental results from places like the Large Hadron Collider now is that it's possible that the Higgs field value we have now is not the sort of final answer, right? It looks like the Higgs field might be what we call metastable, which means that it's set up at this state that it's in, but that's not the sort of preferred state. Sort of like if you take like a teacup and set it on the edge of a table, like right at the edge, it's fine, it's sitting there, but if something bumped it, it would fall down to the ground and it would smash on the floor. And so in some sense, it kind of wants to be down there on the floor. That's the preferred state. And sticking it up on the edge of the table is asking for trouble, right? Like that's not, but at the same time, the only way you can drink your tea and the only way the teacup exists is if it's sitting there on the edge of the table. If it goes to the floor, everything's a disaster. And we seem to be in a kind of similar place in the universe potentially, where the Higgs field is at this metastable state, and something could happen that could kick it down to its preferred state, which is a set of laws of physics where we cannot exist. There's more technical explanations I could go into, but that's the basic idea, that the Higgs field might be this, fundamentally unstable where it's at. And the positive thing is that there are only a few ways we could change the Higgs field, that the Higgs field could change, right? So one of them is, in principle, it could be disturbed, just like you could knock your teacup off the table. In practice, we don't know of any mechanism for that to happen based on our understanding of how events work in the universe. People used to worry that, maybe a high energy collision like at the Large Hadron Collider could disturb the Higgs field and kick us into this other vacuum state. We know that can't happen for several reasons, mostly that there are much higher energy collisions happening in space all the time, and they haven't kicked our Higgs field down. So the other possibility is a quantum tunneling event. So you can think of the Higgs field as being a little ball in a little valley, right? Okay, so imagine there's a little valley and there's a little ball at the bottom of that valley. It's sitting there, it's totally stable, it's fine. But imagine that little valley is actually just a divot in a deeper valley, and there's some lower valley below that, and our Higgs field is just sitting in this little divot up here. So it could be kicked over this hill, or it could stay there forever. Or if you have a quantum mechanical universe, a universe where there is some uncertainty to energy and position in subatomic particles all the time. And if you imagine that this Higgs field is governed by subatomic physics because it's an energy field and it's a basically subatomic thing, it's a microscopic thing, then it's subject to that same uncertainty. So quantum tunneling is an event where, and I know that this is an area of your research. So quantum tunneling is where you can have a particle on one side of a barrier, and it could suddenly just appear on the other side of the barrier without having to go around without having to go through, it just kind of shows up on the other side. And this is something that's weird about quantum mechanics, and it happens all the time. And we use it as a technology all the time. It's part of how flash memory works with computers and so on. It's just part of, we make microscopes based on this principle. The Higgs field is subject to that uncertainty and that quantum tunneling possibility, which means that if it's sitting in its little valley, little divot on the side of the valley, it could quantum tunnel through that barrier at any moment and roll down and be at the bottom and change how physics works in our universe. And the way that would happen is that somewhere in the universe, the Higgs field at one point would undergo that tunneling event, and it would sort of knock all of the Higgs field around it into that lower valley too, which created a bubble of a different kind of space, what we call a true vacuum. And that true vacuum bubble would expand through the universe at about the speed of light. And inside that bubble would be a set of rules of physics where our bodies cannot exist, where molecules and atoms cannot exist. And everything it touched would be thrown into that new set of rules of physics and totally destroyed. And then we think also, it turns out that the space inside that true vacuum bubble would be gravitationally unstable. So once you come into the bubble and your molecules are destroyed, then you also collapse into a black hole.
You said it could happen at any time. So obviously, people are thinking, hang on a minute. Technically, at least the big crunch, the heat death, the big rip, they're things that we can say are scenarios in the far distant future. But then I guess the saving grace is that it could happen technically at any moment, but if it happens far enough away from us, then it doesn't get to us any quicker than it takes light to reach us, which could be billions of years. That's
one thing that could be a saving grace. I think the more important thing is that it's very unlikely to happen anytime soon. Okay. So with quantum tunneling, as you well know, it's an event where you have some probability for it to happen within a time period, but you can't say for sure if it's going to happen in that time period, right? You don't know exactly when in that time period it'll happen. You just know on average, there'll be sort of this many quantum tunneling events during this amount of time. And so we can do those calculations about the universe. They're very hard calculations. There are a lot of uncertainties. So we don't have a very specific number there. We can say probably, 10 to the power of 100 years from now is about when we'd expect, the earliest we'd expect this quantum tunneling.
Okay, I can live with that.
Which is long after everything in the universe is destroyed through some other means. So right. I wouldn't worry about it. But it is intriguing because it is this uncertain thing, because it is technically something that could happen. And that's, I always try to not scare people and say, look, our understanding of physics is, if it's going to happen, it's probably going to be 10 to the 100 years from now. Also, we don't know for sure if this is even the case, because there's a lot we don't understand about how particle physics works, and maybe something else will go on. But it is that sort of little uncertainty about it is intriguing.
Right, I'm aware of the time, and I did want to ask you a little bit about science communication and so on, and actually it's on Twitter. But we better sort of round this off, because we did say there are 5 scenarios, and the fifth one is this possibility of a cyclic universe that it bounces from one generation, and we just happen to be within one of those cycles.
Yeah.
I mean, I know there are some people like Roger Penrose, who are advocating a form of, a model for a cyclic universe. I mean, what does that involve? And how likely is that scenario?
Well, I tried to bring together a few different possibilities in that chapter, because there are several different ways to imagine a universe that cycles from beginning to end to new beginning, and so on. So Roger Penrose's cyclic cosmology, conformal cyclic cosmology, is one possibility, where in that theory the universe evolves to a heat death, and then a new Big Bang comes out of that. So it's a you sort of have an ending and then a new beginning in that direction. There's also my PhD advisor, Paul Steinhardt, came up with some colleagues an idea of a cycling universe that sort of contracts and then re-expands. And so you have either a real big crunch or just a sort of smaller contraction, but then a process happens that creates a new Big Bang out of that. And his original idea for that involved involved collisions of universes that caused that new Big Bang, which is a sort of more dramatic picture. But the new version is a slightly different way of doing it. But either way, you get a sort of contraction and then a new Big Bang. And then there are some ideas. There's a new one also from some colleagues of mine in Canada, where they have a sort of pre-universe that transitions into a present day universe. So you had they call it an anti-universe, universe anti-universe pair, where there was an anti-universe that ended and then caused our Big Bang. And that's sort of a newer idea that's still being sort of developed. But there are a few of these possibilities, and most of the ways that you come up with a cyclic universe is by thinking about the beginning of the universe and trying to understand how our universe got set up in the way it did at the beginning. Because basically, coming back to this question of entropy, we know entropy has to increase over time because of the second law of thermodynamics. But if we measure, the entropy in the universe today, and we think about how low it must have been at the beginning to set up everything, so it's been increasing over time, it seems like the entropy of the universe had to be weirdly low. And then that suggests that something maybe set up that situation. And that's where you get these cyclic universes, something to explain why the entropy of the universe was so low at the beginning, what set up the initial conditions, and then led to the universe we see now. So there are a lot of really intriguing ideas in that area, and they're all kind of still being developed and explored. But it's a nice idea that we have some kind of renewal, at the end.
Yeah, I mean, and I guess it chimes with a lot of religions like Hinduism and so on, where the things that time is cyclic. And I think what is nice and also sort of slightly frustrating sometimes of some of the ideas in theoretical cosmology is that people come up with these ideas and come up with a model scenario, and they write up a paper that goes on what's called a preprint list, and then by the time it's going to get published, oh no, I've moved on from that, I've got a new idea, because it's obviously it's very hard to test. I mean, we touched on this before. What would you need to measure? What data would you need to? And some of these ideas are really hard to test. One of the things I just quickly before we finish, I wanted to ask you about was one of these ideas that a lot of people working on, mathematical physicists are working on, which is hard to test, is string theory, which is essentially not about the very large, but about the very small, and the ultimate building blocks of the universe, and bringing in all the different forces of nature, bringing gravity in with quantum mechanics. And I get the sense that in the book that you were a little bit skeptical about it, because string theory, while very powerful mathematically and beautiful mathematically, doesn't necessarily describe our universe. And you're really keen on knowing what our universe is about.
Right. Well, so I think what I was trying to say with that is that the methods that are currently being used to explore string theory and the models that are being produced, a lot of them are being produced in a mathematical framework that doesn't fit the number of dimensions our universe has, or the history of our universe, or the way that space-time is set up. And that's because we're still in this state in string theory where the calculations that would apply to our universe are still just too hard. We don't have a framework that matches it to what we see in our universe. So, the people who are working on string theory are working on these sort of incremental steps to find something that could apply to our universe. So the mathematical framework is still being put together, and it's a complicated thing because the experimental situation with string theory is very, very tough, because you're talking about energy scales, length scales that we can't reach with our current experiments, and so it's unclear how to test it right now. There's not a really obvious way to test these ideas of string theory, and theoretically it's still being understood. Like we're still trying to find a totally consistent model that matches the way our universe is put together. So it's not that I think that, I don't want to cast shade on string theory, but it's just such a hard problem, and it's hard from both sides. It's hard on the theory side, and it's hard on the experiment side, and it's not clear yet how it's going to all turn out. Are we really going to find that string theory is the answer, and we'll find a way to test it, we'll find a way to make it consistent with our current the way that our universe is structured, or are we going to maybe get some insights from string theory that'll point us in the direction of some other theory that better describes our universe? And we don't know yet.
I mean, that's the key, isn't it? That we simply don't know yet. There's I'm sure you're aware, there's that famous article by Stephen Hawking back in 1981 or so, asking whether the end of physics is near, because towards the end of the 20th century, we thought we were very close to sort of having a theory of everything. And yet, you've talked about, we don't know what dark matter is, or we don't know what it's made of. We don't know what dark energy is, what its properties are. We don't know whether some of these ideas about how our universe evolved are true. And that, so we're further away probably from a theory of everything than maybe we thought we were 40 years ago.
Yeah, I mean, we've discovered so many new mysteries since that time that we thought we kind of knew what the universe was made of. And back in, if that article was 1981, since that time we discovered dark matter and dark energy, which are the two most abundant things in the universe. Those together, they account for 95% of what the universe is made of. We were working with 5% of the universe at the time. We're like, oh, we have this figured out. No, so it's, we're learning more all the time.
It was much better to be talking about this just fascinating stuff than anything else, really. So I'm not disappointed that we've not left much time for anything else. But I mean, I should say, I'm sort of quite jealous that you have twice the Twitter following that I have. In fact, I think among physicists really around the world, I think it's probably only people like Neil deGrasse Tyson and Brian Cox that have bigger followings than you. I don't know that some of the US physicists, there's a few maybe.
Yeah, there's a handful. I think depending on whether I count as a physicist or an astronomer, I'm somewhere in the top 10 of that list.
But you do have this prominent sort of a public profile. I mean, given that you're mostly your interest is in this very sort of esoteric, very complex area of science.
Yeah.
Do you enjoy, trying to get it across, particularly, on a medium like social media, like Twitter, where you only have so many characters? Is it a challenge that you like, answering people's questions or getting across some of these ideas? Succinct soundbite.
Yeah, it really is. It really is a challenge I enjoy. I think that it's, I mean, it sounds pretentious to put it this way, but I think Twitter it's a literary form, right? It's a way of structuring a thought that has certain restrictions and certain, limitations, but also, there's also a very immediate feedback that you get from it, and it can have this really great reach. And so it's a way for me to think about how to express ideas in a way that will reach people, that will make people think, that will intrigue people to want to learn more. And there are certain advantages Twitter has. I can embed images and links and send people to more information. And the sort of immediate feedback and conversation of it, I know what people are interested in hearing because they tell me. I know what people are confused about because they tell me, and I know what people get excited about because they spread it around and they include exclamation marks and all of that. So it's a way to be really interactive in a way that I appreciate a lot. And I think it's done wonders for my abilities to do science writing and science communication, because I have this direct line to what confuses people, what excites people, what people want to tell their friends. And so it's been a fantastic resource from that perspective. I mean, in terms of thinking about, coming up with explanations that are going to be accessible to people, that's very clear when you tweet something, because if you put out a tweet that is unclear or confusing, you will immediately have 10 people saying, I don't get this. What is this about? And then you have to answer that. You have to revise. And so there's a huge incentive to make it very, very clear the first time, and to constantly be improving how you explain things, such that more and more people will understand it, will get out of it what you're trying to put there. And so so that's really, really valuable. And then just, hearing, a lot of what I do on Twitter is just listening to what other people are saying, and find out what are the concerns people have, and I talk a lot about things like the structure of academia and social issues and so on, and I hear from people what are things that are particularly challenging, what are things that are unjust and need changing, and all of that, and I can get involved in those conversations as well. And so that's also really important to me.
Well, I think this past hour certainly may have helped people get more out of some of these ideas than what you could, with all your talents, put into a tweet. I hope people have enjoyed it, and I really do recommend people get the book and read it. I thoroughly enjoyed it. I have to read my favorite bit from the book, where there's a bit you put in capital letters, sort of Trumpian Twitter style, say, but it gets even stranger. Then you say, I'm sorry for shouting, I really am, but I'm not going to sugarcoat this. The universe is freaking weird. And then you go on to explain some of the weirdest aspects of it. So I mean, it's however complicated these ideas are, that doesn't mean there can be less inspiring, entertaining, informative, and enjoyable to read. So despite the current pandemic and lockdown and what the world is going through now, I wish you and the book the best of luck. You can't go on a book tour at the moment, but hey, let's hopefully maybe later on in the year things will up. I hope you've enjoyed the hour. I hope everyone else who's been listening in has enjoyed this. So Katie Mack, thank you very much indeed for your time. And
thank you.
It's been a pleasure chatting to you. I was saying before we started, we've corresponded on Twitter, but we've never actually spoken face to face, albeit on Zoom in this way. Thank you everyone for joining us, and please everyone tune in to other events at the Science Festival, because there are others not quite as fascinating and brilliant as this past hour has been, but almost as nice. Thanks everyone. Goodbye.
Thank you so much. This was great.